Hello everyone, welcome back. So, let us continue our discussion. We are in week 1 and this is our lecture 2. Before we discuss today's topic, let us quickly review what we discussed in the last class. So, we talked about elasticity and then we also discussed Hooke's law. So, if we consider a material which is ductile in nature and for that material the stress strain behavior what you can see on your screen. Now, obviously, for this case we start from this initial position and then as we increase loading then the stress varies along with strain and it follows this path. Obviously, in the initial part sigma stress is proportional to strain, this we have already discussed, and then the proportionality constant is what we call Young's modulus of the material, right. Then once it reaches this point A, beyond that it is no longer proportional. So, then it follows a curved path and we reach a point B. This point is what is called yield point, right. So, this particular location. So, if we draw the corresponding sigma, so this is yield point. Okay. Then beyond that, if we keep on loading, what will happen? For a small change in stress, large change in strain occurs, right. And this is the plastic deformation of the material, and beyond that again the point C, beyond this point again the stress increases along with strain and ultimately it reaches this point E where the material fails. So, this is the point of fracture. Then this point D is what is called the ultimate load carrying capacity of the material. So, this is sigma ultimate. And if you recall, we also discussed that if we take a specimen which follows certain standard and then using UTM, if we apply some loading, then beyond this point C, what happens? At the middle, the cross section of the material reduces and this is what is called necking. So, this is the plane along which the material fails, it breaks there when we reach the point E. But along this form line, the stress that we calculate here, the sigma, is based on the original diameter of the material, which beyond the point C reduces, and that is denoted by this dotted line. So, you can see here actually the D, the diameter of the material is it's less than what we started initially. And obviously, if we consider that reduced diameter, let us call it dr, then we can trace the path shown by this dotted line and ultimately we will reach this E prime. So, up to this point we discussed in the last class and we also discussed this material behavior which is defined by this constant and that is called Young's modulus. So, the example of this ductile material is basically steel. The content of carbon in steel governs its material behavior. So, if we increase the percentage of carbon, then obviously the material behavior changes. So, it starts from ductile to brittle. So, material type we have in this discussion are mentioned here. One is ductile, another is brittle. We will mostly deal with this type of behavior, ductile behavior, but let us also consider the stress strain behavior of a brittle material. So, this is what you can see is the stress strain behavior of the brittle material. Obviously, as we load the specimen, so you have a specimen, and then if we keep on increasing the load on this specimen, we actually follow this path. Now, if we look at the stress strain behavior, we do not have distinct yield point that we can notice from this particular plot. So, for this type of structure, what we do? We consider a point on the strain axis. So, this is the point as you can see on your screen, and then we draw a parallel line shown here by this dotted line, and we reach a point. Now, this line, the one shown by this black dotted marking, is parallel to the original stress strain behavior of the material, and this is what is called 0.002 offset line. So, the strain here at this point is 0.2%, and we get this point here, say this is A and here it is B. So, this A corresponding to this 0.2% offset line is what is the yield point. Beyond this point, obviously, the material shows plastic behavior, and you can also identify the point where the stress is maximum. So, that is how the brittle material behaves. Now, what we have noticed from this discussion that different material, they have different types of stress strain behavior. So, for that we make a specimen, then apply this load P. We know the gauge length and we know the diameter. So, we can calculate the strain. Strain is nothing but change in length over initial length. Remember, this is the gauge length, and we can use different gauge length that we discussed in the last class. Depending upon that, we get different strain. For this discussion, let us consider the initial gauge length, and we can calculate this strain, and then we can also calculate the stress, which is P by A. Now, not all the materials, they show linear behavior, as you can see in this case. So, we have a material whose stress strain behavior is shown here, and that is shown by this pink line. Now, for this case, we have a loading path and we have an unloading path. So, initially we start applying this P, that means we follow this loading path. So, it moves along this path, and then after a certain time we start removing the load, and then it follows the same path, and once we remove the complete load, it reaches the initial point where from we started. Now, here also we can identify that A and B point, as you can see on your screen, as we discussed in the previous case, but the only difference here is that stress and strain are not following a linear relation once we start loading, but it follows the same path during its loading and unloading. So, that is the point to be noted. Obviously, if we go beyond this point A and we keep on loading, then we reach ultimately a point E, and the region say O E prime, this is the region where we have elastic behavior, and beyond this point we have plastic behavior. So, this is another pattern of stress strain behavior that we notice. Now, not every case we have this loading and unloading path exactly similar. What does it mean? If we take a material and then start loading it, then we can stress the path that the stress versus strain follows. So, here you can see by this pink line. Now, initially we have loading. So, as we keep on increasing, we reach a point say A, and then after crossing that we reach a point E, as you can see on your screen. But in the previous case, from E, as we start removing the loading, we actually can trace back the path and we can reach 0 once we remove the complete load. But here in this case, if we start unloading, instead of following the initial path, it actually follows a different path, as you can see, and it reaches a new point which is not 0. So, this is the unloading path which is followed by the material. Obviously, in this case, this initial part is basically the residual strain that is left within the material once we have a complete loading and unloading cycle. And obviously, we can identify the elastic and the plastic region which is defined by this point E. So, beyond this point here, everything is following this plastic behavior, but before that we have a elastic recovery which is defined by this part. So, this much of the elastic strain we can recover, but the material has a residual strain which is marked by this line, say, which reaches A prime. So, following this unloading path we reach A prime. So, O A prime is basically the residual strain. So, what is the difference between the material say here number 1 and material number 2 is that in case of material 1, every loading and unloading cycle brings back the material to 0. But in the second case, a loading and unloading cycle actually offers a residual strain which is denoted by OA prime. So, if we design a structure using a material which follows this material behavior, obviously, we have to make sure that we deal with this residual strain here. Okay. So, let us move forward. Now, we have already discussed this ductile behavior and also the proportionality of stress with strain, right. So, stress is Young's modulus times strain. Okay. So, this we have already discussed. Now, if we consider a prismatic bar and we apply a force P, as you can see here, then there is a gauge length. So, we have the initial configuration, so which is shown by this dotted line, right. So, this is the initial configuration. Okay. On this initial configuration, we apply a force of magnitude P, and as per our sign convention, this is positive. So, P is tension. The cross section of the material is say circular with a diameter of d, and we have the gauge length which is capital L. Obviously, the moment we apply this P, the material will elongate, and this is the amount of elongation which actually defines the amount of strain. So, this is delta L. Now, not only the material elongates along this direction, but it also contracts in the orthogonal direction. And this actually causes a lateral strain. So, we apply a force of P in the longitudinal direction. However, the moment we apply this force P, there is a lateral strain developed in the material. Now, how much is this reduction? We can actually mark it as delta D. So, the axial strain is equal to delta L by the gauge length. So, what about this lateral strain? This is equal to, so say this is epsilon axial L, and then here it is lateral. So, this is delta D by the initial diameter. And obviously, axial strain as per our configuration is positive, and therefore, this lateral strain it is negative. Remember, P acts uniformly over the section. That is the first assumption, and the second one is material is homogeneous. Then we have two different strains, axial strain and this lateral strain. The ratio of these two is what is called Poisson's ratio. So, this is the ratio of lateral strain and axial strain. So, now we can quantify the strain in the orthogonal direction with respect to the applied force P. And we define another material property which is called Poisson's ratio. Okay. So, earlier we defined Young's modulus, and now we have Poisson's ratio. And what are the assumptions? As you can see, P is uniform over the cross section, material is homogeneous, and also it is isotropic. Okay. So, let us see how this lateral strain is developed within a body. How does it affect the volume of a material, right? So, what we will do? We will consider cuboid, and then using the definition of Poisson's ratio, we will see what is the volumetric change in the material. So, volume change under uniaxial tension. So, what we do? Let us consider a cuboid. So, it has dimension A, B, C along x, y and z axis, right. And what we do? We apply a stress which is uniaxial stress. Now, just note the difference. Earlier we applied force, here also we have force, but instead of force now I mark it as the stress along the direction x. So, we have uniaxial tension. Initially, this dotted line shows the configuration of the material. And once we apply this stress along x, which is tensile, Because of this stress, there is an elongation along x axis, and for that there will be a reduction in the dimension along y and z axis. So, you can see the initial marking and the final dimension of the material. So, the volume denoted by say V initial is what? It is A times B times C. Now, the length A is increased by an amount epsilon times A. So, that is the net deformation along x. Similarly, we can also find out the deformation along y and z axis. So, we can actually find out final volume. So, for that we have the new dimension along x is A times 1 plus epsilon. Then other two dimensions B and C, they have also changed. So, B is now 1 minus epsilon, because due to Poisson's effect, this will be Poisson's ratio times epsilon. So, due to Poisson effect, the dimension in the orthogonal direction has reduced. Similarly, we get C, which is 1 minus Poisson's ratio times the strain in the direction of the applied force. So, we can simplify this, we can collect A, B, C, and then what we have is 1 plus epsilon, then 1 minus gamma times, or sorry, nu times epsilon whole square. So, if we further simplify, what we have 1 plus epsilon, then here we have 1 minus 2 times epsilon times nu plus epsilon square. Now, because epsilon is a very small quantity, so this we can neglect. So, what ultimately we have is A B C times 1 plus epsilon times 1 minus twice nu epsilon. And then we can further simplify this. So, we have A B C, and then if we multiply, so the first term is 1 plus then epsilon minus so that is the final expression. So, what we can see, we have again epsilon square and this is small, so we can neglect it. So, ultimately what we get after simplification is that the net volume is this quantity. So, we can find out the change in volume, which is delta V, which is nothing but V final minus V initial. So, if we do that, we are left with therefore, we get E, which is the volumetric strain, and that is delta V by initial V initial. So, what we have is epsilon times 1 minus 2 nu. If you recall, sigma is equal to E times epsilon. So, what we get E is sigma by capital E times 1 minus 2 nu. So, that is how the material deforms in 3D once we have a uniaxial tension. And as you have noticed, because of the Poisson effect, we have change in volume, and that is quantified here. Okay. So, let us move forward. Now, not only we have uniaxial strain acting over the material, we have stress also along the two planes parallel to each other, and then what we get is what is called shear stress. Earlier we discussed axial stress and now we have shear stress. So, if we consider a body as you can see here, and the two opposite face is having actually force acting along this surface, then it will also cause some stress because this force is acting over the entire area, and that stress which is acting over this surface is called the shear stress, and it is denoted by tau. And under these stress, how the material will deform? You can see the deformed shape of the material which is shown here. So, what we get is the shear stress tau average is equal to, again say V is the force acting over the area. So, it is V by A. Now, shear stress is of two types. One is called direct shear stress, another is indirect. But one thing you must note that shear stress is acting along two planes which are parallel. So, along this plane and the one at the bottom, these are the two planes along which this force is acting, which are equal in magnitude, but opposite in direction. Now, let us take a different example. So, here you can see we have three plates which are connected by this rivet. So, we apply some force here and that also develop, say we apply a force P1 and then here P2, P2. Now, all these plates are connected by this rivet, and if you look at the loading configuration, we can identify the stresses acting on the rivet. As you can see here, these are the three regions denoted by this pink arrow, where the stress originating from different plates are acting. Now, if we consider a section, say this segment, and then if we draw the free body diagram, then obviously we have the stress here, and because we cut along these two planes, obviously we will have shear stress developed here. If we look at plan, again it is a circular section. Obviously, over the entire region, entire cross section, we have this shear stress acting. Now, you can ask me where is the component which is in the opposite direction of this arrow. It is actually acting here in the upper section. Similarly, in case of this tau, another shear stress component will be acting here, and this is a case of direct shear. So, we have a different case where shear stress also develops within a material due to, say, for example, bending of a beam. So, if we have a beam, so this is the beam, and if we apply a force at the middle, obviously it will deflect like this. So, this bending of the beam will develop shear stress at every section. As we progress in this course, we will study this behavior, we will quantify also that, and that is the example of indirect shear stress. For the time being, let us focus on direct shear stress, and as we progress, we will consider this type of elastic body, and then we will also consider their deflected shape, and we will quantify the stress components that are developed due to the action of some external force. Okay. So, now again let us consider the same cuboid, but in this case what we have shear stress acting on the opposite faces. So, you can see we have tau here on this face, and along the opposite face we have tau in the opposite direction. Obviously, if there is no shear in these two planes, what will happen? Because tau, which is separated by distance of delta x, will actually develop a couple. What is the couple? So, if I quantify that as m, so tau times the area over which it acts. So, the dimension of this cuboid is delta x, delta y, delta z. So, this plane over which tau acts is delta y times delta z. So, they are the forces acting on this face and this face, which are separated by a distance of delta x. So, that will develop a couple. Now, the stress tau 1 along the other two parallel faces of this cuboid will actually balance this couple developed by tau. And we can also quantify that couple, say this is m1. So, that is tau 1 times over the area, that is delta x times delta z. So, that is the force which is multiplied by the lever arm. So, in this case it is delta y. So, what we have is tau 1 times delta x, delta y, delta z. So, that is the volume of the cuboid, right. Now, these two quantity, they must balance each other, otherwise there will be a rotation. So, m must be equal to m1, which in other case it actually proves that tau is equal to tau 1. So, what we conclude? The two faces, a plane is defined by its perpendicular. So, this is the x plane, and this is the y plane. So, along x plane, the shear stress is tau, and along y plane, the shear stress is tau 1, and they must be equal in magnitude. That is what we get from this derivation. And these two shear stresses tau and tau 1, they face each other, and that is how they maintain the equilibrium, so that there is no rotation caused by this shear stresses. This is called equality of cross shears. Very important property. We have to keep in mind that cross shears, in this case it is tau and tau 1, they are equal. Now, for shear stress also we have to define the sign convention. Remember, in case of axial stress it was tension positive, compression negative. The question is, what is the sign convention in case of shear stress? So, for the shear stress, first we have to define the plane over which it is acting. So, let us consider this X plane. Okay. So, let us focus on X plane. Now, how it is defined? Again, a plane is defined by its normal. So, we define this plane by its normal, which is along the positive x. So, that is the positive direction, right. So, this is positive x plane. Similarly, if you come here, this is the negative x plane. Okay. Now, if you look at the direction of this tau, which is also along the positive direction, right. So, it is acting over the positive plane and it is acting along the positive direction. So, that is positive. So, positive shear stress is acting along the positive face and positive direction. So, that is the sign convention that we will follow in case of shear stress. So, when we will go further, I will elaborate more on this, but keep this in mind that in case of shear stress, first we have to identify the plane, and then once we identify the positive plane and the negative plane, and on that plane we have to see along which direction the force is acting, that will give us the proper sign of the particular shear stress. Okay. Now, in case of shear stress, again as you can see here, again we consider the same cuboid of dimension delta x, delta y, delta z. We can define Hooke's law . So, we have shear stress which is proportional to shear strain. So, we have to define shear strain, and for that again we consider the same body over which the shear stress is acting. That will cause a deformation, and you can see the angular deformation. So, this gamma is called the shear strain. So, that is the shear strain. So, the moment we define Hooke's law for shear stress or shear strain, so tau is proportional to gamma. And if we remove this sign, what we will get is tau is equal to g times gamma, and g is called the shear modulus. So, we have already defined Young's modulus, Poisson's ratio, and now we have G, capital G, that is the shear modulus. And what is the interrelation between them? G is equal to E divided by 2 times 1 plus. So, that is the relation. We will actually derive this relation as we progress in the course, but for the time being let us consider this expression what actually correlates shear modulus, Young's modulus and the Poisson's ratio of a particular material. And these are the material properties very important for homogeneous elastic isotropic material, and we have to remember these expressions for all our problems. We will solve actually some problems in the next class, and we will quantify these material parameters as we progress in this course. So, with that let us close here. Thank you very much.